Another thing that we can use derivatives to do is to find the concavity of a function. Before speaking to the intuition of concavity, let's give it its proper definition first. A function is said to be concave down on the interval AB if whenever we draw a tangent line on that interval, the line lives above the graph of f. Correspondingly, the function is concave up if every tangent line lives beneath the graph. Let's draw a generic function to see what this means. Now, concavity says something about the curvature of a function, in a sense whether it's opening upwards or opening downwards. This function here seems to be opening downwards on the left and upwards on the right, with a switch somewhere in between. This should be our intuition for concavity. To tie that intuition to the definition above, choose any point on the concave downside and draw the tangent line. Note that on the concave down interval, the green tangent line always lives strictly above the blue function. In a similar sense, drawing the tangent on the concave up region results in a tangent which always lives beneath the function. And it's important to note that I'm not saying that the tangent will live beneath the function everywhere, just on the portion where we claim that f is concave up. Also, I feel I should mention that there is a definition of concavity that does not require our function to be differentiable. However, it's much more complicated. The points where the concavity of a function f changes, we're going to call those inflection points of f. In this example above, we can eyeball the inflection point as being where this green line meets the x-axis. We'll use inflection points to help us find the intervals where a function is of constant concavity. But before we do that, let's relate concavity to derivatives so that we have a tool to help us compute them. Let's suppose then that f is twice differentiable on the interval I. If f double prime is non-negative at every point on that interval, then f is concave up on that interval. In the dual sense, if f is non-positive at every point of that interval, then f is concave down on that interval. A useful tip that I use to help remember this is to draw two faces. One happy face with positive eyes, because being positive corresponds to being happy, and a negative face with negative eyes. In this case, the smile tells me the concavity, so the positive eyes corresponding to a positive derivative admits a concave up function, and vice versa for the negative eyes and concave down functions. Moreover, the theorem tells us that points where the second derivative is 0 or does not exist are probably going to be good candidates for inflection points. So let's put this to work then with an example. Let's determine the intervals of concavity for the function x squared over x plus 1 all squared. To do this, we're going to need to find the second derivative. This is good practice. I'm going to go through it quickly, but you may want to pause and see if you can get the same answer. We'll use the quotient rule to get the first derivative, and with some convenient cancellations arrive at this. And we're going to have to appeal to the quotient rule again for the second derivative. This one's a little bit messier, but again, there are some nice cancellations. By inspection on the second derivative, we see that it'll be 0 when x is equal to half, and will fail to exist precisely when x is equal to -1. These are our candidate inflection points, so let's check the sign of f double prime around these points. Note that the denominator x plus 1 to the power of 4 is always non-negative, so we can determine the sign of f double prime just by checking the numerator. Doing so gives us the following result for the signs of f double prime. Thus, by our theorem, we know that f is concave up on -∞ to -1 and -1 to a half, and is concave down on 1/2 to infinity. This makes x equals 1/2 our only inflection point. Thus, by looking at the second derivative of a function, we can infer something about the curvature of its graph.